Good morning and welcome to the EAI International Conference on Cognitive Computing and Cyber Physical Systems IC4S 2020. On behalf of the organizing committee, I, Dr. Nishu Gupta, the conference chair of this event, welcome all the participants, researchers, scientists, academicians and students from all over the world to participate and present their research work in this conference IC4S 2020. Well, it's pretty unfortunate that we could not meet in the physical format to attend this conference as it was initially planned due to COVID-19. Nevertheless, we have gathered today to attend this conference in virtual format. The success of any conference solely depends on the hard work being put by the members of the organizing committee, the technical program committee, and various other committees constituted for the successful organization. At this point, I extend my heartfelt thanks to Professor Sara Paiva from Polytechnic of Viana do Castelo, Portugal, and Professor Manuel Gabriel Reis of Portugal, along with the conference manager Ms. Viltare, for extending all their support, encouragement, and comments at various stages throughout the process of bringing up this conference. This conference received various high-quality submissions, which, after rigorous review process, were selected for presentation and acceptance in IC4S 2020. I am highly thankful to the organizing committee, the members of the Smart Summit 360 for extending their cooperation, along with the members of EAI and all those who are directly or indirectly involved in bringing out this conference. With these words, in the capacity of the conference chair, I declare this conference open for discussion and presentation, with a firm belief that we'll meet again in the physical format in 2021. Thank you.
Dear ladies and gentlemen, let me welcome you to the EAI IC4S 2020 conference held in this virtual interactive setting. I am Viltare Platzner and I would like to address all of you on behalf of EAI and IC4S 2020. I would like to use this opportunity to address the organizing committee, the authors, and all the participants on behalf of all of us here at EAI. I would like to thank all of you for being a part of this conference and for your involvement with EAI. In particular, I would like to thank the general chairs, Dr. Nishu Gupta and Tushar Khare, together with the whole organizing committee, for their excellent work during conference preparation. Today, during this streaming, we would like to invite you to participate in the Q&A sessions. During each video, please write your questions about the current presentation into the chat window. After the presentation is done, the session chair will ask selected questions to the author of the presentation in a live conversation. Lastly, I like to use this message to invite you to join us again at the EAI IC4S 2021. Should you be interested in becoming a part of the next year's conference, please do not hesitate to contact us at the email address below. Similarly, if you are interested in discussing other possible cooperation, conference, a workshop, or a new event altogether, please contact us at this email address as well. Thank you for your attention and enjoy EAI IC4S 2020.
Hi everyone, my name is Michal Dudic. I'm the community manager at EAI, European Alliance for Innovation. It's my pleasure to welcome you at this conference and say a few words about who we are and what we can do for you and your research career. In short, EAI is a global community for a greener, healthier and smarter world. As of today, we are home to more than 60,000 members from 167 countries, and we reach out to tens of thousands of subscribers. As an organization, we are nonprofit from day one, and what is most important to us is that we remain open to all researchers from all around the world thanks to membership that is completely free. We organize more than 100 events annually, such as this conference, and we do so in publishing partnership with Springer. I said in the beginning that EAI is a community, so let's talk about what that means and what it means for you. To put it briefly, we give our members a platform that builds their research. We do it with 3 main online community services where members come together to help each other write a better paper, get an objective review, and get recognized fairly. The 3 services in question are EAI Compass, Community Review, and EAI Index. Firstly, EAI Compass is an online app where you can meet and connect with new colleagues and get feedback on your paper as well as your presentation. In addition to that, it lets you download all full papers that will be presented at this conference, and you can vote on your favorite presentations as well as see everyone who is here and connect with them. You can do this right now if you go to EAI Compass website, compass.eai.eu. Next, we are improving the classic conference review process with community review. It has already been in use at all our events since 2019, and we were very excited to hear a lot of positive feedback from program committee members regarding the reliability and the speed of the community review. Let's talk briefly about what community review does. Essentially, it is a website that shows abstracts of papers that are right in the middle of the review process, as long as the authors allow it, of course. And all EAI members may then bid to review specific papers. When they submit their bid, they put in their bio and their qualifications, which are sent to the program committee, who can then decide whether or not this bidder is qualified to review the paper they bid on. This relatively easy access to review opportunities means that bidders really need to put their best foot forward if they wish to be selected, which improves the quality of the entire review process. At the end of the day, this benefits you, the author. And last but not least, let me tell you a thing or two about EAI Index. EAI Index is our credit-based evaluation system that we rolled out this year to all of our conferences and journals that allow you to climb the global ranks of EAI community and get recognized for your work. It calculates a number value for most actions you make, such as getting your paper accepted or submitting a review, and these numbers accumulate for 12 months. At the end of this 12-month period, we put together a ladder of all EAI members, and the ones at the top receive a nomination to one of the membership ranks: senior member, distinguished member, or fellow. For each action that is eligible for EAI Index credits, we'll look at the quality of your action as it was evaluated by another member of the community, such as, for example, the review score of your submission. To make sure that the system is fair to newcomers, every 12 months the credit count gets erased, the ones at the top receive their nominations, and every member starts at 0 for the following 12 months. And finally, Smart Submit is a collaboration feature that is coming later this year. It will allow you to submit your research ideas and your work in progress abstracts to get the kind of help and feedback you're looking for. Maybe you are looking for co-authors, maybe you would like to find a mentor or a mentee, or maybe you want to find out how the community feels about your idea. This is what Smart Submit is designed for. Ultimately, it's about helping you write a better paper and increasing your chances of getting accepted. Again, we will be launching this feature later this year, so stay tuned. And so I'm going to leave you with many different ways to get engaged at different levels. There are lots of opportunities in many of our events and publications, which means many ways to connect with people and collaborate. You may learn more about everything I just talked about at our website, eai.eu. These services exist to help you and to make your lives easier, so we encourage you to send us your comments, ideas, and feedback to community@eai.eu. And if you're interested in volunteering and contributing, you can let us know at the same email address. Don't forget that you can use EAI Compass to vote on presentations in real time to determine which ones are the best, as well as to download all full papers that will be presented today. Just make sure that you log in using the same email address as the one you used to register to this conference. Thank you very much for your attention. Please enjoy the conference, and I hope we will see everyone online soon.
Hello everyone, my name is Jinhua Yu from Tongji University. Now I'd like to introduce our research about automatic generation of security requirements for cyber-physical systems. The co-authors of this paper are Professor Wagner from University of Stuttgart and Professor Luo from Tongji University. Firstly, I'd like to introduce the motivation of our research. Security is a very important property of cyber-physical systems, and security analysis is an essential step of system security design. It can identify security requirements and guide further security design. And normally, we perform the security analysis manually. This is an example outcomes of a security requirement analysis. We have to identify each insecure items concept by hand and fill in these outcomes tables. Also assign each labels and descriptions of it. And the whole process is time consuming. And if we find some mistakes in the later stage, we have to find each related point in these tables and correct them one by one. This is time consuming and sometimes boring. So we considered, can we make this analysis process automatically? So the main purpose of our research in this research is to find ways to identify security requirements automatically. Before I go into our concrete approach, I'd like to introduce some background knowledge to you. The first one is, what is STPA? STPA is a safety analysis technique based on the STAMP model. Here is the general workflow of this STPA approach. There are 4 steps here, and the highlights of this approach is it shifts from focusing on preventing failures and avoiding threats to enforcing safety constraints and control system vulnerabilities. Although this is a security analysis techniques originally, there are also several extensions of STPA and make the STPA framework works in different kind of domains like STPA-SEC. This is the STPA-based approach for security analysis. The STPA-SafeSec is the approach for the integrated analysis of both safety and security. The STPA-Priv is the STPA-based approach for the privacy analysis. And the main approach we based on is the adaptation of the STPA-SEC, which is called STPA-DF-SEC. It is a data flow-based adaptation of STPA-SEC. This adaptation is proposed in our previous research, and this adaptation can fit the data flow-based system better. This approach follows the basic STPA framework, and there are still 4 steps in this approach. The first one is define the purpose of the analysis, which include identify the whole system losses, the system vulnerabilities, and the constraints at a high level, at a very high system level. And then we will model the functional interaction structures of a system. Here is some example structures of these, the so-called functional interaction structures. we will display the functions, the main functions of each component of these systems, and link these functions with these arrows, and these arrows represent the data flows between different functions and different components. After we have these structures, we can then identify the insecure functional behaviors. We can identify these behaviors with some guide words. There are three guide words proposed in this approach. They are being executed, not being executed cause vulnerabilities, being executed but cause vulnerabilities, and being executed but exceeding the time limits caused vulnerabilities. And after we identified these insecure functional behaviors, we can then identify the loss scenarios for each insecure functional behaviors. And also, we provided guide words for the identification, like the guide words are the function itself, the environment, including the function imports, the calling behaviors, the computing resources, and the links. This is the basic security analysis approach we used in our automated generator. Now I'd like to introduce the concrete methodology of this automated generator. Here is the overall workflow of this automated generator. The first two steps are the same as the manual analysis process. But after we finish the second step of the STPA DFSEC, after we model the functional interaction structures, we have to fill in a questionnaire here. And then we can generate the IFB matrix by one click, the insecure function behavior matrix. And then we can check this matrix manually and adjust it if there are something that you want to change. And after we get this IFB matrix, we can generate IFB tables, the insecure function behavior tables by one click. And by another click, we can generate the loss scenario table finally. So let's see these steps one by one. First is the questionnaire. Here is the questionnaire for the generator. Each questions in this questionnaire are actually the conditions for generating corresponding items in later phase. And the designer, the analyst have to fill in this questionnaire for each function. Like function 1, you have to answer this question, these 9 questions, and for another function, maybe from function 2, you also have to fill in answer these questions. And these questions are used as conditions for generating. And just like here, this whole workflow is the workflow of generating IFB matrix. And in this subflow of IFB type, here is the judgment. Here is a place that the generator need to judge whether we need to check the type conditions, and these conditions can be get from this questionnaire. For example, this is the IFB type and condition tables. For example, the type 1, the IFB type 1 not being executed type is related to this condition, and this condition is related to the question 4. So according to the answer of this question 4, the generator can decide whether this condition, whether this function match this condition or not match this condition. If this condition is matched, the generator will mark y a yes in the matrix in the certain place. Otherwise, it will mark n a no in the certain place. And after we perform all these process, we can get an insecure function behavior matrix. It looks like this. So each of these y or n mark are decided by the questions in the questionnaire, and each row in this IFB matrix represent a function. So after we get this IFB matrix, we can check whether the result, whether you are satisfied with this result, whether these results are correct according to your understanding. You can adjust them by hand, or you can leave it like this. And after we get this IFB matrix, we can then generate the IFB table. Here is a button called Generate IFBs. So after we click this button, the IFB table will be generated here. And here is the loop of each IFB tab. So for each IFB tab, like for each column, it will check the mark type. If it is a Y, it will add a IFB label. Here is the IFB label, which is automatically generated, and also add a description of the corresponding label. For example, in this IFB table, this label VEF1 IFB1 represent the function data check is not executed. And this another example like IFB2, which represent the description of this IFB2 is the function data check is executed with information leakage risk. And from this IFB matrix, here's another button which is called Generate Losses. So after we click this button, we can get the loss scenery table like this. And here is the main flow of generating the loss scenery table. The generator will also check each pattern conditions and decided whether it is matched, whether the condition is matched or not. Like if it is matched, it will add a loss scenery label like this column, or like this column, and also the corresponding description like this sentence in this table. And the loss scenery patterns and the conditions are also provided in the paper. Here is the example for the IFB type 1. There are two loss scenery patterns, and the first one is the function is bypassed intendedly, which can be detected by the user. And if a function is support this IFB type 1, and it will automatically match this condition, and this loss scenery pattern is automatically matched by default. So if the function supports this type, this loss scenery will be appeared in its loss scenery tables. And for the second loss scenery patterns, the function is bypassed intendedly and outputs a fake result. Here is the corresponding conditions of these loss sceneries, and then this number represents the related questions in the questionnaire. So whether this condition is matched or not will be obtained from the questionnaire. So after we go through all these steps, we will finish our security requirement analysis automatically. So after we fill in the questionnaire and after a few clicks, we can finally get output. So it's much easier than writing all things by hand and check and assign each labels into these tables. And then after we finish the prototype of this generator, we try to conducted some experiments and also try to evaluate our automatic approach. So we planned to analyze the same system by both manual and automated ways and try to compare the outcomes of these two different kind of analysis. Here is the system under analysis. We performed the analysis based on two kind of system. The first one is in-vehicle diagnostic and a software update system. This is a system that try to transmit the data between the in-vehicle components like the ECU, the electronic control unit, and the external devices like the handheld device or the manufacturer's cloud. And another system is the Bluetooth digital key system. The purpose of this system is to use smartphones to lock or unlock the doors of a vehicle. And the analyst of these two analyses are the same, which means the same authors did both manual and automated analysis, which makes the outcomes of different analyses comparable. And during the experiments, we record the time consumption of the analysis and also record and compare the number of final outcomes. So let's discuss about the results of the experiments. First, here is the time consumption of both analyst process. The blue box are the time we used in the automatic analysis, and this orange box are the time we consumed in the manual analysis. It is really obvious that we use much less time in the automatic analysis. And we calculated that we use about 1.7 minutes per function to finish the requirements. And what we need to do is only fill in the questionnaire, review, and adjust the generated IV matrix and plus a few clicks. And besides, it's also spent much less time for the modification. If we find some mistakes in the final tables or some misunderstanding in the later stage of the analysis, we can quickly quickly modify, revise the initial input and generate the correct outputs immediately. And besides, we also we also compare the outcomes of the different analysis. Here is the example. We list the low scenery labels here together and compared the outcomes one by one. We found that one output in one analysis may be mapped to several in another analysis. For example, this label in the automated analysis can be mapped to two labels, two loss scenarios in the manual analysis, or by contrast, the same loss scenarios can also mapped the same loss scenarios in the manual analysis can also be mapped to different labels in the automated automated analysis. So we cannot just simply calculate the numbers, count the numbers in different analysis. If we need to get some reasonable result from these numbers, we have to compare them one by one. And besides, there are some understanding errors that may affect the comparisons. For example, in the automated analysis, we may think that a function A is related to the confidentiality. But when we do the manual analysis, we may think this function is not related to the confidentiality. So this may result in the understanding errors, because although we perform the analysis by the same person, but the understanding of a problem, of issues may also varies at the different times. So in order to reduce the bias in our comparison so we also remove the understanding errors in our comparison analysis. So after the careful comparison of both of the outcomes of both analysis, we get these final comparison results. We can see that for the IFB, for the insecure function behaviors, the numbers numbers obtained from both automated and the manual analysis are almost the same. Only one new IFB is newly identified in the automatic analysis. But for the loss scenarios, there are more new loss scenarios can be identified by the automatic analysis. So we evaluate our approach based on three metrics. We found that the proposed approach, the automated generator, is much efficient. It requires much less time to generate the final outcomes. Second, it's more effective. The proposed approach can cover all the manually identified outcomes, and it can also find missing points of the manual analysis. The third one is the automated approach is much more flexible. It can easily to modify the input information and generate the corresponding outcomes. If you find mistakes in your later analysis state or in the final loss scenario tables, you can fix it very quickly. Just modify the input informations, and then you can get the correct outcomes immediately, instead of to check whether. By contrast, in the manual ways, you have to check each point related to these mistakes and modified it by hand. We also find two limitations of our proposed approach. Firstly, since this approach, the automated generator depends on empirical repository of a system. Those lociner patterns, the conditions are extracted from the empirical studies empirical analyze. So if we need to analyze new types of system, if based on this automatic approach, we required more professionals and also take much time to build a high quality repository for the generator at the beginning. And the second limitation is the generated description of the automated way are more general, and it do not have too much details about the specific things of these systems. So further requirement are further refinement are required for further design work. Finally, let me summarize our research. First, in this research, we propose an approach based on STPA DFSEC to achieve security requirements automatically. Second, we developed a prototype by using Excel VBA to implement this concept. Third, we conducted experimental analysis of 2 cyber-physical systems in the automotive domain to evaluate the automated approach. We also planned some future works of our research. First, we will analyze more related systems in practice to improve the pattern repository or our approach process. Second, we will design a software tool for better use experience features. In our proposed prototype, it just realizes the functions. It just works, but if we want to use this approach to support the real work of the engineers in the industries, we need to design a better software for with better use experience features. That's all I'd like to introduce, and thank you for your attention.
Hello, my name is Nicolo Zaboglou, and I'm a postgraduate student in the Master Program Advanced Technologies in Informatics and Computers, hosted by the Department of Computer Science and International Hellenic University in Greece. In this presentation, I will present you the results of our survey paper, Privacy-Preserving Blockchain-Based Solutions in the Internet of Things. Let's start with a summary of this work. This survey paper's focus is to provide an insight via a search process in the existing literature on the proposed solutions regarding privacy-preserving issues in the Internet of Things. The list of solutions presented here is not meant to be an exhaustive list for the domain. We only analyze those that were specifically proposed for the IoT and therefore address the peculiarities of that environment. Although blockchain technologies have been extensively studied, to the best of our knowledge, there has been only one similar work about blockchain-based methods that facilitate privacy preservation in IoT. However, this work focuses only on 2 issues, the device authentication and the decentralized identifiers. In this paper, we present a wider range of privacy-preserving blockchain-based solutions in IoT and categorize them according to the topic in which they proposed the solution and the approach they used. This presentation comprises, in background, research methodology, privacy-preserving blockchain-based solutions in IoT, discussion of the identified solutions, and conclusions. In this part, I will start with some background details that are adequate for a better understanding of this work. Internet of Things is a promising, relatively new technology that develops smart networks with a variety of uses and applications. The diversity of protocols, technologies, and devices that IoT consists of, even though they add in value and utility, they create major privacy issues that can be exploited by malicious entities to benefit from or even violate privacy of IoT users. The special features of blockchain technology, such as immutability, transparency, accessibility, autonomy, and decentralization, has led the academics and the industry to search for further uses of it, besides financial applications that was initially applied. The IoT ecosystem comprises many applications and services that can be combined with other edge technologies such as machine learning, big data, and blockchain technology to provide the so-called smart environments with promising results. The amount of user-related personal data being generated, processed, and transferred in the diversified IoT deployments attract a lot of unwanted attention by threat agents who target, among others, users' personal data. This figure depicts a typical example of a user IoT ecosystem with privacy challenges. Privacy. It is hard to define privacy, the right to be let alone, the right of the individual to decide what information about himself should be communicated to others and under what circumstances, the right of informational self-determination. Privacy is also sometimes related to anonymity, but in information technology it is known as information or data privacy and refers to the development of relationships between technology and the legal right to or public expectation of privacy in the collection and sharing of personal data. Privacy restrictions typically stem from applicable legal frameworks. For example, in the European Union, the General Data Protection Regulation, GDPR, has come into force to create an even higher level than before of privacy protection within the EU and gave citizens control over their personal data. Given the volume of the personal data being handled by IoT devices, it is easy to understand that the GDPR has many implications to many IoT domains. Blockchain is an append-only decentralized digital public ledger based on cryptography. A record of all the transactions that take place inside the blockchain is being maintained in a chronological order in a distributed database in the form of blocks in a chain. All the participating nodes in this peer-to-peer network get a duplicated copy of the blockchain database. When the participating nodes agree on the validity of a transaction and the requirements of the consensus algorithm have been satisfied, a time-stamped block is added to the blockchain. After a block becomes part of the blockchain, it is nearly impossible to tamper with it. Accordingly, the overall blockchain framework consists of 4 layers as depicted in this figure: the application layer, the consensus layer, the data layer, and the network layer. The applications layer includes all the features, applications, and uses of blockchain. The consensus layer includes the consensus algorithms such as proof of work and proof of stake that are utilized by the various blockchains. The data layer is self-explanatory, and the network layer handles all the connectivity matters of blockchain. The applications of blockchain vary and include financial services, healthcare, rights management, IoT, and security. The key features of blockchains, such as decentralization, transparency, open source, accessibility, autonomy, and immutability, make them very attractive to many environments as they can successfully address significant security requirements. Still, though, there are privacy challenges that need to be considered when applying blockchain technology. The research methodology that we followed consisted of 2 main steps. First step, extensive search in the research literature maintained in Scopus search engine, a certified academically approved tool. The goal of our search was to find explicitly the related keywords of privacy and blockchain in the title of the papers and the related keywords of IoT in the title, abstract, and keywords. The exact query, which was used in April 2020 and returned 96 relevant papers was the following. Second step, by studying the title, abstract, conclusion parts of each of the above papers, we were able to narrow down even more the relevant to our subject papers. In this step, we excluded papers that were addressing specific sectors of IoT networks, and we focused on papers that had potential solutions in wider and more generalized application in IoT. This plot demonstrates the yearly distribution of publications that deal with privacy solutions in blockchain technology, the number of publications per year that we focus on this paper based on the query of our methodology, and the percentage of the second one in the first one for each year. This demonstrates the interest that the research community shows on the use of privacy-preserving blockchain solutions in the IoT ecosystem. Based on these statistical results, we infer that the global interest in this kind of solution is rising and gaining ground fast, with the amount of relevant to the matter papers almost doubling each year since the publication of the first research paper in 2017. In this part, I will briefly present in chronological order the solutions that were identified in the literature by using the previously described methodology. Let's start now with the first solution, that is called Fair Access. Fair Access is a privacy-preserving blockchain-based access control framework for IoT, which combines access control and cryptocurrency mechanisms. Through the use of encrypted authentication, tokens enforced by smart contracts, an IoT device owner can manage access rights and policies in a flexible and easy-to-apply manner. The encryption of token is performed using the built-in elliptic curve crypto system. Fair Access addresses several IoT privacy and security requirements such as decentralization and lightweightness. Although some issues in IoT are successfully addressed thanks to Fair Access, some other critical issues emerged. There is a discrepancy between the sensitive and private nature of access control policies and the transparent and public nature of blockchain technology. Traceability, allowing third parties to detect thing-to-thing communication patterns and authorization functionality patterns. The usage of blockchain-connected gateways was proposed to preserve users' privacy by providing access to the data of IoT devices according to a given preference policy. The blockchain gateways play the role of a mediator between users and IoT devices. Users can acquire the information and privacy policies of an IoT device connected to a gateway and access the device through it rather than directly. Consequently, the blockchain gateway impedes the device from obtaining personal data unless users accept the device's privacy policies. The data stored in a blockchain infrastructure is tamper-resistant, so users' preferences can be utilized to resolve disputes between users and IoT service providers. The use of decentralized attribute-based encryption, ABE, proposed to preserve confidentiality and privacy of transaction data in blockchain-based IoT applications. This method utilizes more powerful devices than IoT sensors to perform computationally expensive operations on their behalf. The transaction data can only be seen and verified by entities who have the right attributes. The entities involved in the proposed scheme are cluster heads, blockchain miners, attribute authorities, and the blockchain. The cluster head encrypts data to target the particular miners and the right attributes. The blockchain miners verify the transacted data and the transaction itself. After that, they mine, add new blocks to the blockchain, and get rewarded with tokens. The attribute authorities have to verify and issue credentials to distinct users and miners according to their attributes. CapChain is a privacy-preserving access control framework for pervasive environments based on blockchain technology. CapChain allows users to share access rights for devices they own via tokens. Capabilities are generated and encrypted by the device's owner and transferred by appropriate anonymous transactions that take place on a public blockchain. Device owners have full control over the delegations they provide. To ensure the privacy of the participants, CapChain adapts well-established techniques such as obfuscation to hide capability ID and ring signature to avoid unauthorized capability commitment. An overview of the access rights delegation process is shown in the figure. CapChain employs a similar idea to transfer authorization tokens through transactions such as fair access and is affected by anonymous cryptocurrencies. PPDAC is a lightweight and privacy-preserving access control framework based on blockchain technology to assure in-depth access control functions for IoT devices with strong anonymity guarantee for IoT end users. The proposed scheme meets IoT security and privacy needs while overcomes the challenges in integrating blockchain to IoT. PPDAC is integrated over fair access. The reason why the author has developed PPDAC scheme was to strengthen users' anonymity and to maintain transparency features in fair access. Additionally, to enable untraceability of authorization tokens, it is introduced a zero-knowledge succinct non-interactive argument of knowledge (ZK-SNARKs) protocol. To sum up, the provided approach respects principles such as security through transparency, user-driven policy, privacy by design, and edge intelligence. Advocate is an innovative platform proposed to satisfy the GDPR requirements about users being able to control their personal data, be informed, and consent to processing by third parties. It also helps third parties wishing to access such data to meet the requirements of the regulation. Advocate focuses on the management of devices that users own and manage their personal data protection policy and consents. An intelligent policies analysis mechanism utilizes intelligent adaptive technologies to identify contradictory or conflicting rules and policies related to the disposal of private information and ensure that this cannot be used for user profiling. The consents management component responsible for providing integrity, versioning control, non-repudiation, and validity of data subjects' consents and data controllers' commitments is based on a blockchain. Signed consents to data control to the ledger without, however, disclosing any details about the users' identities or the devices they handle. The authors do not bind their architecture to a specific blockchain solution. They rather focus on the consensus algorithm, and they suggest the use of a proof of authority one, which requires less messages exchanges and offers better performance. SecureSVM is a privacy-preserving support vector machine training scheme over blockchain-based encrypted IoT data. SecureSVM addresses the challenging task of incorporating blockchain into a machine learning training process. The first challenge was to design an appropriate training data format. The second challenge lied with the elaboration of a training algorithm. In comparison to previous works, SecureSVM combines the pi-layer cryptosystem with blockchain techniques to address the concerns about data privacy, integrity, and ownership. So the proposed scheme can be used without the need of a trusted third party and is able to train SVM classifiers without accuracy loss. The authors concluded that with SecureSVM, each data provider is unable to acquire any knowledge regarding the data of other providers, while the data analyst's model parameters are also kept hidden from data. Trust Chain is proposed to overcome issues related to energy consumption and delays found in traditional blockchain architectures. IoT devices do not have the enormous energy resources required to verify each block of data in the blockchain. Trust Chain does so by combining the power of blockchains with trust concepts. Trust Chain is designed to increase the privacy of its participants while improving the effectiveness of services. The main difference of Trust Chain to other conventional blockchains is the application of computational trust. It develops a novel lightweight consensus management protocol by combining this trust with the Byzantine fault tolerance protocol. Indicatively, to evaluate the provided trust, it measures the reliability of participating parties before creating smart contracts and initiating interactions among them. Additionally, Trust Chain delegates the edge computing architecture of IoT due to its durability with low storage and computing resources. Finally, Trust Chain embeds unique techniques to improve privacy when dealing with sensitive personal data and complies with GDPR legislation. A permissioned blockchain to address privacy protection and energy security in smart grids is proposed. System provides transparency and traceability on users' energy usage without, however, revealing participating nodes' identities. Users are identified by pseudonyms. Storing data on the permissioned blockchain facilitates data protection, while access authorization is secured by the use of traditional access control methods. Edge nodes and user identities are registered with a group signature algorithm and validated by a supernode using covert channel authorization. The use of group signatures facilitates anonymity as nodes in the group do not know each other's identity, but only the identity of the supernode which is responsible for organizing resource allocation. Figure depicts the main activities that take place in the PBEM-SGN proposed blockchain. The authors provided in a practical proof of their proposed scheme on Ethereum using the standalone client Gith and Ethereum wallet. Privacy sharing aims to facilitate data sharing in smart cities while protecting users' privacy and providing data security. Authors utilize the channels mechanisms of the Hyperledger Fabric platform to control access to specific types of data by a group of authorized organizations. The adoption of multiple channels provides increased privacy of user data but also scalability to their proposed solution. Access control to user data is further secured by smart contracts, which allows data exposure to stakeholders on the need-to-know basis. Moreover, privacy sharing complies with some of the most significant data security and privacy requirements of the GDPR. Furthermore, the solution provides data integrity, tamper resistance, and non-repudiation. Privacy sharing grants secure client access to the blockchain network through a REST API. It also defines a reward system for users sharing their data with stakeholders or third parties with a local digital token named PrivaCoin. Finally, their experimental results verified that the multi-channel blockchain solution scales better than a single-channel blockchain system. Ethereum is a scalable, high-performance blockchain scheme providing security and privacy for the industrial Internet of Things. The model aims to overcome problems in IIoT such as high computational complexity and latency challenges. Their proposed mutual multi-factor authentication and key establishment protocol uses a time-based zero-knowledge proof-of-knowledge scheme combined with authenticated encryption. In the node's registration phase, Ethereum relies on Peterson commitments to assign them digital identities. The TZK-PK usage mitigates Eclipse attacks where proof of work and proof of stake are vulnerable. A local blockchain is used to record all transactions. The experimental results reveal that Ethereum has low computational complexity compared to existing relevant schemes, and in terms of latency, it meets the required IIoT latency target. A hybrid blockchain scheme for trustful billing and charging transactions in IoT, energy, and utility market is proposed. The infrastructure consists of a main blockchain and sub-network blockchains. The introduced bridge, which links the main blockchain to its sub-networks, isolates users' peer-to-peer transactions and provides user anonymity. Also helps avoid user profiling and identification by entities of the upper layer of the smart grid. Peer-to-peer transactions within credit sharing groups in microgrids are handled by local blocks. The author simulated a use case scenario of a smart building to evaluate the performance of their proposed solution. A differentially private multi-party data sharing model for machine learning purposes in IIoT applications that is based on permissioned blockchain is proposed. The actual raw data is not directly shared among the parties, but used for building data models based on federated learning algorithms. Additionally, authors present a blockchain-based architecture that allows collaborative data sharing over the multiple parties located distributively in order to reduce data leakage risks. This decentralized architecture continues to support data owners to keep the control of their data and to provide selectively access to it. In order to enrich further the provided privacy, differential privacy methods are integrated into federated learning by adding appropriate noise in the local raw data. Also, the proposed approach is evaluated for its effectiveness in two real-world datasets for data categorization. The results show that the increasing data providers has little effect on the accuracy, while the running time is obviously increasing. Nevertheless, the authors do not provide experiments with any custom or real blockchain infrastructure. In this part, I will discuss the most important issues emerging from our work and that can be useful to future research. As it is presented in the table, the majority of the proposed solutions focus on access control as a privacy-preserving provided service utilizing public blockchain infrastructures. These solutions include fair access, blockchain gateways, PPBABE, CapChain, and PPDAC. Private sharing, on the other hand, provides the same service based on permissioned blockchain. All of these solutions lack evaluation, with the exception of private sharing, which provides both a security analysis and extended experimental results. Another group of solutions are more application-oriented and focus on privacy in energy transactions, like HighBridge, which uses algorithmic techniques such as data suppression and generalization, and PBEM-SGN, which uses group signatures. Both solutions provide sufficient experimental results. However, evaluation on a large scale would provide a better feasibility assessment. Privacy-preserving solutions for machine learning in IoT data is proposed in SecureSVM and BFL-PPDS. SecureSVM utilizes homomorphic encryption to achieve user data privacy, a most frequently used method amongst the proposed methodologies. BFL-PPDS introduces a new approach which utilizes federated learning and differential privacy. Both of the proposed services provide only partial experimental results, which need to be expanded to also cover blockchain technology aspects. Finally, there are other proposed solutions in the literature which look at the investigated topic, each of them from a different point of view, such as Advocate, which utilizes blockchain technology to provide consent management of IoT data, Zerium, which looks at distributed multi-factor authentication in IIoT, and TrustChain, which processes a permissioned blockchain in IoT. Each of these topics needs to be further explored by the research community and requires extended evaluation. In this survey paper, we presented privacy-preserving blockchain-based solutions in the IoT environment that address personal data protection and preservation of user privacy. In our analysis, we described the identified solutions and we compared them in regards to the focused IoT area, the applied blockchain infrastructure, the provided privacy-preserving service, the utilized underlying privacy mechanisms, and the implementation level. Blockchain technology, as revealed from the results of this paper, is recently adopted as a solution to cover various privacy issues related to the IoT, and so it is not odd that many of the proposed solutions are still in theoretical or early development stage, with less than 50% providing implementation details. So it is paramount that in order to provide viable solutions and attain a better grasp of the matter, further research and exploration has to be conducted from the research community. We would also like to thank the Master Program Advanced Technologies in Informatics and Computers hosted by the Department of Computer Science, International Hellenic University, Kavala, Greece, that supported this effort and funded our participation in the EAI IC4S conference. Thank you for your attention.
Hello, everybody. This is Manuel Cabral Reis speaking, the last author in the authors list of the paper, a non-intrusive IoT-based real-time alert system for elderly people in monitoring. During my presentation, I will go through an introduction where the developing context and the aims of the system are presented, followed by the presentation of the system requirements and its description. After that point, I will present the tests that we have conducted and the results we have achieved. Of course, that my presentation will be concluded with a conclusion section and future work. So, all over the world, people are living longer, and it is prognosed that in Europe, by 2060, one third of the population will be aged 65 and above, with many of them having some kind of disability or limitations, requiring for the different forms of care. Unless a big change is introduced, the limited number of caregivers will not be able to respond to the care demands. So, as such, providing high-quality care services is becoming one of the biggest challenges of contemporary societies. One possible solution is to use the, assistive technologies to support people in their own homes or even in assisted living facilities. There are two main objectives in the ambient and assisted living research area. To know monitoring solutions providing information used for detection of emergency situations, like, for example, a fall or an illness, and for detection of symptoms indicating that such situations may happen in the future. And the other is the direct support of elderly people in their everyday life. The first one, monitoring, can be implemented using positioning systems, which may also produce useful information about the elderly person's health. Consequently, the development of monitoring systems should be made having in mind the aim and place where the system will operate. Obviously, that the resulting information can be used for different purposes, being activity monitoring one of the most used. The collected data allows for the determination of physical activity periods. For example, information on walked paths can be used for behavior analysis, like the determination of occupancy periods of particular rooms, for example, the one that we'll use in this project and this paper. And walking speed, like the analysis of data in time domain, for example. The information of the gait speed is very important because it depends on the health stats of the elderly people. One must also have in mind that the elderly person gait speed is typically very low, usually not higher than 1.2 meters per second, and values lower than 0.6 meters per second increase the likelihood of health issues. Well, these systems can also be used in other type of impairments, such as wandering patterns, typical of people having mental issues. But later analysis helps to detect abnormal situations resulting from health problems or accidents. The processing of the collected data will allow the comparison of the person's behavior or the people behavior against an assumed model. The difference between the model and the current person's behavior may be used to trigger alerts that are usually sent to the caregivers of the monitored person. The purpose of the collected data has crucial implications on the requirements concerning the tracking system's accuracy. For example, in case of activity or room occupancy evaluation, determination of position with the room accuracy is sufficient. However, if the system is used to gate velocity tracking, positioning matter or even submatter accuracy is crucial, whereas for wandering detection, the precision of localization results is of paramount importance. The acceptance of the system is the most important and crucial factor. Determining the success, this will effectively determine the success of the monitoring. But also preserving privacy, trust, declared functionality, and low cost of the devices and services are obviously on the top of the list of elderly users and caregivers acceptance criteria. If the devices performing the monitoring are to be aware by the elder person, its use must be accepted by the user. One way to gain elderly users' acceptance is to provide the user with a wide variety of forms of tags and ways of wearing. For example, simply carry it around in a pocket, using wristbands, pendants, devices attached to a waist belt, etc., etc., etc. Obviously, the size and the weight of the device should be minimized. But also obtrusivity of the system infrastructure is another very important factor. A typical infrastructure of the monitoring system consists of several sensing nodes performing the measurements. These sensing nodes are the ones who perform measurements, and the controller, the one that processes the measurement results, calculates the locations of or localization of the elderly person, or more precisely, the location of the tag, etc. The systems are typically deployed in an already furnished home, and so any change to the interior design, such as connecting the device with cables or moving the furniture, should be avoided. Another important issue related to the system exploration is the tag's energy consumption. However, because the system presented here does not rely on the use of any kind of tag, this issue will not be discussed here. The environment where the system is installed has a significant impact on the tracking accuracy and the system reliability. For example, building materials, pieces of furniture, and other interior design elements determine the propagation condition influencing the signal's delays and levels. This may reduce the performance of the system, may reduce the performance of the system. In such cases, tracking errors can be reduced, for example, by changing sensing nodes locations. Now, concerning the system itself, the system proposed here aims at being a real-time, non-intrusive, IoT-based alert system for monitoring elderly people. Activity and room occupancy evaluation are really its major concern. So that determination of position with room accuracy is sufficient. Additionally, the system is to be developed using simple and low cost off-the-shelf electronic components. However, it is also intended that this solution can integrate other monitoring components commercially available on the market, such as bracelets or measuring heart rate devices, video cameras, robots, for example, for medication intake, and others, etc., among others. In this figure, we can see a general conceptual overview of the system. As can be seen, the detection sensors are wirelessly connected to the gateway controller. In the case presented here, passive infrared sensors, PIR sensors, the bed sensors and the panic button are all connected to the gateway controller. The gateway controller is connected to a cloud server. If no activity is detected for periods of time superior to the ones established and stored in the database, an alert SMS will be sent by the server to the mobile application installed in the smartphone of the caregiver. The caregiver uses this app to get real-time information about the status of every sensor, the latest detected activity, etc., 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 and also receive alert SMS. As can be seen, this system is conceptually divided in two main concepts and two main components, the hardware component and the software component. In the hardware component, all the different types of sensors and devices are included, like, for example, the passive infrared motion sensors, water flow sensors, switch sensors, door opening sensors, bed movement sensors, panic button, etc., etc., etc. But also included here is the gateway controller with the pre-processing and communications capabilities. Note that the system is intended to work with all these and other sensors installed, or with just one type, for example, the motion sensors. In fact, the results presented below, next in my presentation, were obtained with the system presented in the previous figure, using only motion sensors, one bed sensor, and a panic button. The software component was designed using a server-side application and a mobile smartphone application. The server-side application includes the databases, where all the data sent by the detection sensors are stored. The data stored in the databases include the sensor's name, the identification, the ID, and its location, and for each activity detection, the ID of the sensor who have triggered the detection, and the date and time of the detection are stored also. Included also here are the server-side applications. Here in the server-side application are the software models responsible for the detection of the potential alert situations, which trigger the sending of SMS to the caregivers. For example, typically an elderly gets up in the morning, leaves the bed, goes to the bathroom, and then she or he goes to the kitchen to prepare its breakfast. But if no activity is detected on the kitchen sensor after, say, 50 minutes, nor any movement is detected in the bathroom at the end of this time, then an alert SMS is sent to the mobile application. In this figure, we can see the state machine implemented during the tests presented below, reflecting the possibility of alert situations that can occur. For example, if the sensor bed detects activity and the corresponding peer sensor, the movement sensor, installed in the bedroom, detects no activity for a period longer than 5 minutes, the system enters the sleep mode state. This state will be lived only if the movement sensor or bedroom sensor detects any activity or the total number of configured sleeping hours is achieved. In this case, if no activity is detected by the movement sensor and the total number of sleeping hours is exceeded, then an alert SMS is sent to the caregiver. Note that the state of the sleep can also be entered, for example, after lunch, where typically the elderly person sits on their sofa to watch a little televisions and end up falling asleep. However, in this situation, the total sleeping time will typically be much lower, and the corresponding alert SMS will be sent if this different time threshold will be exceeded. Each of the individual state has a different alert threshold time and triggers the sending of alert SMS when that value is exceeded. It should also be noted that the system keeps periodically resending the alert SMS if no activities detect the situation continues to be verified. By using the mobile app, the caregiver can check the status of the different sensors in real time, check for the last room in the house and time where the activity was detected, and set different threshold times for each of the state's rooms, receive and read warning SMS, among other things. To test the principles and function of the proposed system, we have implemented the practical situation depicted in the previous figures in a real house, a flat, in fact. We have not used sensors presented in bedroom 2. In fact, this room was locked. And the corresponding state machine is presented in the state machine that I was previously explained. And the IoT hardware components are the ones presented in a table below that will be shortly present. In this particular case, all the detection sensors and controller were using wireless communications, so there is no need for the installation of cables or any other kind of home works. All the sensors are powered by the grid network using power adapters. These sensors can be battery powered, but then they have to be periodically replaced with all the associated problems discussed above. We have used GPRS using a GSM modem with an IoT global operator, Things Mobile, trademark, with a SIM card. For the communication between the gateway controller and the server-side application, and the communication between the sensor and the gateway controller were implemented using RF 433 MHz RXB12 EAN technology superhydron receiver. This receiver used the encoding EV1527. By using the Things Mobile SIM card, there is no need for the installation of an internet pack service by a communications provider with a typical much higher cost. For example, in Portugal, it is typically costs to 20 euros per month, whereas the price of this solution is around 2 euro per month. However, in the house flat that we have already installed or an internet pack services, the system can use it because the board we are using, LilyGo TM TTGo TCall V version 1.3 has already a Wi-Fi embedded model. So In this particular case, the total cost of our IoT-based hardware was around 87 euro. In this figure, we can see a general diagram of the gateway control implemented using only off-the-shelf IoT components. This is a picture of the actual gateway controller implemented using off-the-shelf IoT components. This is a picture of the movement sensors implemented. Also, we have a diagram of the bed sensor activity sensor implemented. Once again, using only off-the-shelf IoT components. And this is a picture of the actual bed activity sensor implemented. This is a screenshot of the app, the applications installed in the caregiver mobile phone, and here we can see that the system is online. This is in Portuguese. It was developed here in Portugal, and this is in Portuguese. In this screenshot, we can see that it was detected activity in the hall at 0 minutes ago, and in this screenshot we can see that was the elderly person was detected in the bedroom, in the bed. These are samples of alert that are all in Portuguese. Alert situations, SMS that were sent to the caregiver. In this table, we can see the components used, the manufacturers, and the price of each IoT-based hardware component that we have used in our experiment. As we can see here, for example, the motion sensor is a Digo with its price around 7 euro. It is here written that this is mandatory, but in fact they are all optional. The only component that is mandatory is the gateway, but it only works with at least one of these also installed. Okay, so the total price is below 100 euros, as we have seen above. Now, as for the results, during the week of tests, we have monitored an elderly person's normal activity by using a surveillance camera system. Then we have compared the alert situations with the grabbed images, and there were no situations of false activity detections caused by the sensors, both from the movement sensors or the bed sensors, and even the panic button that we have used also. Although the movement sensors did not always detect at first the presence or movement of the elderly person in the room where they were installed, the movement sensors, they always ended up detecting the presence of the elderly person following its subsequent movements, the following movements. This fact, in fact, is not a problem for our system, since the presence of the elderly person in a given room of the house was sooner or later always detected, and the time delay of that detection has no influence on the performance of our system. For this reason, the number of times that the movement sensors did not detect movement was not counted nor recorded. The panic button was also tested, and it was functioning well. Fortunately, the elderly person did not have to need to use it in a real situation. We also have tested the changing of the threshold alert times in real time, and no errors occurred. Additionally, all the alerts SMS were correctly sent. Here we can see that the test. This is a screenshot of the app when we have tested the panic button, as we can see here, the red color mentions that the SOS button was the panic button was pressed. Now, as for conclusions, as we can see, we conclude that a non-intrusive IoT real-time alert systems for elderly people has been presented. The system aims at being low cost and made using off-the-shelf electronic components. The system is prepared to integrate other monitoring devices already available on the market, such as bracelets, heart rate bracelets, for example, video cameras, robots, among other devices. The conducted tests, both laboratorial and household tests, have proven the effectiveness of the system, and the system tested has a total price less than €100. In the future, we want to integrate convolutional neural networks with deep learning algorithms in the system in order to identify patterns of behavior of the elderly person and thus automatically adapt and fine-tune the individual threshold times of each state for the sending of alert SMS systems. That is all. I left here our contacts. My contact is the last one. I hope that we have enjoyed my presentation. I hope that you all stay well, particularly with health. Thank you very much.
Hello everyone, my name is Marius Thoma and today I'm here to present our paper which is titled A Smartphone Application Designed to Detect Obstacles for Pedestrian Safety. The research for this particular paper was conducted at the RISE Research Center of Excellence in Nicosia, Cyprus, in conjunction with the Visual Media Computing Research Lab in the Cyprus University of Technology. In short, the work involved creating a smartphone application that uses computer vision and machine learning to help address the problem of pedestrian safety in modern cities. Walking in general is related to the quality of life and should be encouraged since it provides many benefits to both humans and the environment. Firstly, walking is by itself beneficial to human health as a form of exercise. In addition, it provides many indirect benefits that can contribute to human health, such as a reduction in road traffic and traffic noise. Also, by reducing traffic, it helps reduce air pollution, which is a major problem in many cities around the world, as shown in the map here. This has the added benefit that it leads to a reduction of greenhouse gas emissions, which contribute to climate change. The problem is, of course, that walking in cities is often dangerous. This is due to the nature of the design of most modern cities, which puts an emphasis on roads and cars. This, in turn, negatively influences pedestrian safety and leads to accidents and deaths. A recent study by the World Health Organization reported that 26% of all deaths relating to roads involved either pedestrians or cyclists, as the figure shows here. In fact, this particular problem is even worse in the area of Eastern Mediterranean where Cyprus is located. So this is clearly an important problem and something that should be a priority for most cities to solve. The question is then, what exactly causes this problem? Of course, the answer to this question is complicated, and as I mentioned before, it's heavily influenced by how cities are designed and the emphasis they put on cars. Another major cause of road accidents is the presence of any obstacles that block pedestrian routes. Anything that gets in the way of pedestrians has a negative impact on their safety, since it forces them to take riskier routes, and so it increases their chances of getting hit by cars or other vehicles. There are many forms of such obstacles, and they can be anything from temporary roadworks, damages to pedestrian walkways, such as potholes or broken pavements, or even illegally parked cars. In the situation shown here, any pedestrian walking on this pavement will have to step into the street to be able to avoid the car, and in a busy street this can obviously be very dangerous. And so the city authorities should deal with such obstacles quickly to minimize the danger to pedestrians. The issue, though, is that often such obstacles remain unreported and the authorities are simply not aware of them, especially in large cities. So ideally, there should be a mechanism that would allow these obstacles to be reported in a centralized fashion, which would allow the city authorities to deal with them quickly. This problem can be solved through crowdsourcing and specifically through the use of citizen science. Citizen science is a form of science that allows citizens to be directly involved in scientific research projects. This involvement is most often achieved with the use of smartphone applications, which allows citizens to easily report data related to the project they are participating in. This was also facilitated by the recent advancements in computing power available in smartphones, as well as the many available sensors that they have readily available, such as cameras, accelerometers, gyroscopes. The latest iPhone even carries a LiDAR sensor. An example of a successful citizen science app is the app eBird, which allows its users to log bird sightings, and this information is used to track bird populations and migratory patterns. Similarly, the iNaturalist app allows its users to log and identify any plants or animals they encounter, and this information is used to monitor biodiversity. Two other app examples are the Laws of the Night and Noise Tube, which allow users to report noise measurements and night brightness measurements, which are used to track noise and light pollution. With the advantages of citizen science in mind, in this project we built a prototype of a smartphone app that will allow pedestrians to report any obstacles they encounter while walking around the city. The process of reporting should be as fast as possible and not require much effort from the user, so we make use of computer vision to speed up the process. The obstacle reports are uploaded to a crowdsourcing platform for further analysis and can be used by the authorities to keep track of and deal with such obstacles. The app essentially allows the user to take a photo of an obstacle they have encountered and upload it to the crowdsourcing platform. When a user takes a photo, the app instantly analyzes it with a convolutional neural network, so it can help the user choose its type quickly. The CNN we use was specifically trained to recognize obstacles in cities and was trained on a dataset of around 1,800 obstacle photos that were collected last year in the city of Nicosia. The collected photos were annotated manually with bounding boxes using the VGG image annotator tool. The CNN was trained using TensorFlow and was based on VGG 16. It can recognize 15 obstacle types, a few examples of which are shown in the photos here, such as narrow or damaged pavements, potholes, illegally parked cars, etc. To incorporate the CNN into the app, we converted it to the TensorFlow Lite format. The final file size of the model was around 20 megabytes, which is acceptable for use in a mobile app. The photos taken by the user are scaled down and are fed to the CNN for analysis. The analysis is relatively quick and usually takes around 300 to 400 milliseconds. This of course depends heavily on the specifications of the smartphone used, but the CNN works fine even on lower-end devices. The oldest device we tested the application on was from around 2012 and had only half a gig of RAM, but the CNN worked okay there as well, only slightly slower. At the time we submitted the paper, we were using the VGG-based CNN, as I mentioned before, but later on we also used a CNN trained with the same dataset but with MobileNet version 2 as its basis. Since MobileNet is optimized for mobile devices, we were able to reduce the analysis times by almost half to around 150 to 200 milliseconds, while getting similar accuracy rates. So, when the photo is analyzed, we present the user with a list of the top 5 most likely obstacle types as they were ranked by the CNN, as you can see here. Using this method, we can reduce the effort needed by the users, since usually they just have to select the first item in the list and just submit the report. Of course, sometimes the CNN will make mistakes, and in that case, the user is free to select the correct obstacle type from the list, or even type in a new type. We record any such discrepancies between the CNN predictions and the user choices, and we can use those to continuously improve the CNN. The advantage of such a system is that each report is essentially a new annotated photo for the dataset, which we can use to retrain the CNN and continuously improve its accuracy. This sort of feedback loop can be useful in many other scenarios as well. The way we use this setup in our app is only one example of many ways such a system can be used. One can easily imagine generalizing this concept and applying it to any other problem that could benefit from machine learning, and in the process crowdsourcing data collection and annotation, which can lead to the creation of continuously improving machine learning models. A secondary advantage of this system is that the initial model that is deployed does not have to be perfect, but just good enough, since it will be able to become more accurate with more training as more data become available. So, once a user reports an obstacle, that information is uploaded to a crowdsourcing platform for further processing. This platform, called iNicosia, is the result of the work of the DARE MRG team here at RISE. The project aims to create a digital twin of the city of Nicosia by integrating available data into a 3D model of the city. By visualizing real-time and future conditions in the city, the platform will provide solutions for optimizing and planning activities and providing solutions in case of emergency scenarios. The project builds upon the existing Nicosia municipality smart city infrastructure and the platform's high-level architecture is shown in this figure. The ultimate goal of the platform is to set up the proper technical infrastructure that will enable the city's digital transformation, as well as host data and modules for real-life applications, advancing both the research capabilities of the city as well as improving the quality of life of its citizens. The app we're presenting in this paper is intended to be one of the first real-world applications of the iNicosia platform. In addition to the app, the platform so far also hosts other applications and services, including visualization and prediction of road traffic, as well as the visualization of open data concerning the city, such as the quality of life evaluation of various areas based on the priorities of the citizens, and identification of micro-scale events happening around the city from online social networks. This slide shows an early prototype of how the iNicosia platform will work, displaying the reported obstacles to the authorities. This is a map of the municipality of Nicosia, and displayed on it is the number of reported obstacles in subdivisions of the municipality. The interested parties can zoom in and see all reported obstacles, as well as details about each reported problem. Also, a special version of the app will be created that will be tailored to the needs of city workers, the people that will actually be responsible for dealing with the obstacles, and it will show them a live map of the city and the locations of reported obstacles near them. A few technical details about the app prototype that was implemented. It was built for the Android operating system, and we used the Kotlin programming language. The app supports all phones running Android 5.0 and above. The architecture of the app follows the model view model paradigm as shown in the diagram. The app communicates with the crowdsourcing platform over a REST API, and the obstacle reports are uploaded in JSON form. In the scenario where no network connection exists at the time when a user creates a report, the report is added to an upload queue, and its upload is triggered whenever an appropriate connection becomes available. So, here's how the app works. First, when a pedestrian encounters an obstacle, they can open the app and take a photo of the obstacle from within the app. Here, the app instantly analyzes the photo of the obstacle and determines the most likely obstacle types, which are shown to the user to select from. As I mentioned previously, initially only the 5 most likely types are shown, which can help the user quickly choose the correct type. Usually that's all the user has to do. In the meantime, in the background, the app automatically determines the location of the user using GPS and displays it on a map, and so the user doesn't have to worry about specifying the correct location of the obstacle manually. Once the user is happy with the results, they can simply press submit, and the report is automatically uploaded to the crowdsourcing platform, where it will become available to the authorities. In the next slide, I'll show you 2 recordings of the app in action. In this first example, you can see the entire reporting process and how quick it can be. On first launch, the app requests access to the camera and GPS from the user. Once they grant the permissions, the user can then take a photo and select the obstacle type, which in this case the CNN has correctly identified to be an illegally parked car. The app also automatically determines the obstacle location, and so the user does not have to manually specify it. Then, if the user is satisfied that the information is correct, they can just submit the report. Of course, the CNN may not always be correct. In this second example, the CNN fails to recognize the obstacle type correctly, which in this case is a tree. In such a case, the user can select the correct type from the predefined list or even type in a new type of obstacle. The user is also free to edit the location of the obstacle on the map if they think that it's wrong or if they have no working GPS on their device. By keeping the time and effort commitment of the users to a minimum, we hope to increase engagement with and usage of the app that will hopefully lead to safer urban environments and increased pedestrian safety. Finally, in the paper we also report an evaluation we carried out to evaluate the effectiveness of the user experience of the app prototype. The purpose of the evaluation was to help us identify potential areas where the app can be improved and to see how the app actually performs while in the hands of users. 25 volunteers participated in the evaluation by using the app in real conditions while walking in the city and reporting at least 3 obstacles they found during their walk. The volunteers then answered the user experience questionnaire, which was developed by Shreb et al. Precisely for this kind of UX evaluation. The UEQ quantifies the UX experience on 6 scales, as listed here on the table, specifically attractiveness, dependability, efficiency, novelty, perspicuity, and simulation. The volunteers rated the app on a scale of 1 to 7 on aspects of several components of the aforementioned scales. These components are listed in the table as well. The results of the UX evaluation were very positive, since the app received a positive score in all scales measured by the UEQ. The 6 scales are scored on a scale that starts at -3 on the lowest end and goes up to 3 on the highest. The app scored lowest on the perspicuity scale, on which the app scored only above average. The perspicuity scale measures how easy it is for users to get familiar and learn how to use the app, suggesting that the prototype would benefit from improvements on those areas by being less complex and easier to understand. In all other aspects, the volunteers found the app's UX satisfying, which demonstrates the potential of the app to be used in the framework of a smart city and ultimately increase pedestrian safety. So, in conclusion, we built an app prototype that allows pedestrians to easily report any obstacles they encounter, which we hope will help increase pedestrian safety in the long term. We believe that this concept can be easily generalized to other users and can be used to create continuously improving machine learning models. Future work will include further improving the app and addressing the issues identified by the UX evaluation we carried out. Before being released, there are a few obstacles that have to be overcome, the most important among them the issue of the private information in the photos the users will capture. These include information such as faces, car license plates, etc. Ideally, features such as this would be blurred automatically by the app, and so the information would never leave the user's devices. Of course, in this area, other deep learning models can be used, but this aspect must be the subject of further research. Finally, an iOS version of the app should be created, and once the app is finalized, it could be released in app stores and be put to use in smart cities. So, thank you very much for your attention. If you have any questions or comments, please let me know and I'll be happy to answer them. Thank you.
Hello, welcome to the closing ceremony of IC4S 2020. The conference witnessed some very good presentations, novel contributions to the research and technology. So I am here to declare the best presentation award, and based on various parameters, the reviewers found that the paper entitled Automatic Generation of Security Requirements for Cyber Physical Systems is the best paper out of all the papers presented during IC4S 2020. We thank all the participants, researchers, scientists, and everyone who directly or indirectly contributed to this conference, with a firm belief that we'll meet again in physical format in the year 2021. Thank you very much.